oil. Right? For iron extraction, we use four raw materials. Right? Four raw materials. First of all, we have something that contain iron ore, right? So the most commonly used iron ore is Fe2O3, or we call it hematite. Okay. Then we have iron ore. Then we have coke. Coke. Okay, coke is actually something we manufacture from coal. Okay, so we are getting coke from refining of coal. Coal is something that we obtain from earth naturally, and that is containing some impurities, okay, some unnecessary compounds. So there are methods to remove them. After removing those unnecessary compounds, we can get coke. Okay, simply there is something that we get from coal. Okay, and it's not something we obtain naturally from nature. Now let's say atmospheric gas, we can directly use it. There is nothing called coke naturally. Coal is there. From refining coal, we get coke. We get the difference. Clear? And then we use, like I said, atmospheric air. Atmospheric air. From atmospheric air, what we are expecting? Atmospheric air containing majority of nitrogen and oxygen. So I expect to use this oxygen. Like calcium, carbon. So the thing is, Lamai, when they ask to write raw material, don't write the chemical formula. Okay, so when you ask write raw materials, you need to write this raw materials. Now sometimes they are asking the chemicals. Chemicals. What are the chemicals used? Something like that. When they kind of more inclined to ask the chemical substance, then you can write their form. And whenever they ask raw material, we need to give the general name we use for them. You understand? Because, for example, atmospheric air, you can't write O2 because we use atmospheric air. So if you tell O2, it is wrong. We don't use O2 directly. We use oxygen, nitrogen, and everything. So telling O2 is wrong. You understand what I'm telling you? So use these underlying words for raw materials. We're going to discuss about this now. So now we can understand the purpose of hematite because that's where iron is existing. Right? So we are going to extract Fe from them. Right? But for that, what is the purpose of carbon? You might wonder. So the thing is this one. Now listen. For this iron extraction, we are using an setup called blast furnace. Blast furnace. In this blast furnace, we call it as blast because there is a very high temperature maintained. Okay, so books are telling that at the bottom of the blast furnace, we have approximately 1700 Celsius. Or you can say simply 2000 Kelvin. It's a very high temperature. At the top of the blast furnace, books are telling we maintain 400 Celsius or approximately 700 Kelvin. Okay, so 700 Kelvin to 2000 Kelvin, you have a temperature gradient. Okay, so we say usually at this middle line, 1000 Celsius. So this is not a very simple one. It's not a small thing. So it's actually 50 meters, approximately 50 meters in height. Okay, and it has the diameter of several classrooms. And so it's a very big thing. Okay, so in that setup, this temperature gradient is maintained and it is a continuous process. We always can insert solid raw materials from here and we can insert gaseous raw materials from here. Okay, solid raw materials only. And we can continue to add them and we can obtain Fe from the bottom. Understand? So it is continuously happening. It is working 24/7. Always it is working. Alright. Right now, let's try to understand how it is working. Now you know the raw materials and the name of the apparatus, and you know there is a temperature gradient here. You know certain things. Now there is a certain story, just like for any other industry, which we must remember. If you remember that story, you can easily remember this for a certain amount of time. If we remember this one for 2 months, it is enough for us, really. So listen to this story well, and the logic, try to understand the logic, you will be getting it very nicely. Okay. So from the bottom, like I said, we are inserting atmospheric air. So this is heated atmospheric air. Okay. And then from the top, you are adding the remaining three raw materials. So what are the hematite, coke, and calcium carbonate? So we turn them into small particles. Small particles, or you can someone can say powder form. Okay, and we are adding them from the top. Okay, so when we add them as small particles, their surface area is high. Therefore, efficiently they will react, and rate of those reactions will be also high. Understand? And we are sending the air from the downward, and then air will move up, and these particles will move down, and they will meet effectively and react. Can understand the idea and picture? Then I think in this way. So when we add these solid raw materials, one of them, exactly cork, is coming to the bottom. And this cork is reacting with oxygen and forming carbon dioxide. Carbon dioxide. Okay, carbon dioxide. So this is, and this is a highly exothermic reaction. This is a highly exothermic reaction and it releases huge amount of heat. Actually, that's how they maintain this temperature. There should be something, some fuel to support this temperature, support this heat. That heat is given out by this reaction. Is that clear? So, for burns to give carbon dioxide. Okay, like I said, it is an exothermic delta H negative reaction. Okay, delta H negative reaction. Right, then if you think about this further, now this is the interesting part. This carbon dioxide form can react with coke again because you are adding coke from the top. Part of that coke is reacting with oxygen to give carbon dioxide and act as the fuel. Act the fuel. Act as fuel. And another part of that carbon coke is doing this reaction. So these two things are reacting together to form two carbon monoxide. Okay, two carbon monoxide. So one part of this core is spent to form carbon monoxide, CO. Understand? And there's one special thing we must remember today. This reaction's enthalpy change is endothermic. Delta H positive. Okay, that we must remember. And the things you can easily understand if this is acting as a word. It must be exothermic. There is no argument behind that. But here, this reaction, we can't predict like that. And so we should remember it is but endothermic. Understand? Endothermic. Okay, now listen to this one. Some energetics theories have to be used here. And now carefully observe this reaction. And observe this reaction. And tell me the sign of delta S. What is delta S? Entropy change. What is the sign of this reaction is delta S? What do you think? What's it? Why do we think like that? Molecules increases. Number of gas molecules or number of gas moles increases. Okay, so therefore, entropy of the reaction, entropy of the products is high. So when we get delta S by subtracting entropy of the reactants from products, you are subtracting a lower value from a higher value. That will give us a positive answer. Is that clear? Entropy change is positive. Now we can understand where I'm going with this data. Once we know entropy and enthalpy changes, we can predict. But we can predict the spontaneity of this reaction. So what is the formula? Delta H minus T delta S. And delta H minus T delta S. So now we know the enthalpy change is positive, entropy change is positive. Okay. So then what about the minus T delta S? Minus T delta S term is going to be what? A negative value. Okay, so that means we can give a prediction about delta G. So this kind of a reaction will become spontaneous at what conditions? This reaction will become spontaneous at high temperature. That's what we need to have. So when you increase the temperature, T delta S term goes up. At some point, that this negative value can exceed the positive value of delta H. So that gives us but a negative value for delta G. So if delta G becomes negative, this will become spontaneous. So we can say delta G become negative at high temperature. Okay, so this reaction is spontaneous at high temperature. Is that clear? Now listen. Now we don't have any clue about how much high this temperature should be. Okay, so that also we need to remember. At around 1000 degrees Celsius, they have found it by data. At around 1000 degrees Celsius, this reaction is becoming 100% spontaneous. Understand? At around 100 degrees, 1000 degrees Celsius. Okay. At around 1000 degrees Celsius, this becomes 100% spontaneous. It means 100% it is carbon monoxide. Is that clear? You can understand that one easily by looking at the graph. Okay, look at off the page, we have a graph, right? 1000 Celsius there. And what is the y-axis and x-axis in that graph? Y-axis is percentage of carbon monoxide, and this axis is temperature. No? So that graph runs like this. So the percentage is becoming 100%, but after 1000 degrees Celsius. Is that clear? So that means carbon monoxide is the one that exists after 1000 degrees Celsius. I will write that sentence also. After 1000 degrees Celsius. Carbon monoxide is spontaneous. It is. And only carbon monoxide is formed spontaneously after 1000 degrees Celsius. And only carbon monoxide and CO exist after 1000 degrees Celsius. After 1000 degrees Celsius, only carbon monoxide exists. Okay, so that's something valuable to know. Now, what I'm trying to tell you, Lama, even though we get carbon dioxide here, at around this high temperature, what will happen? That all carbon dioxide will react again to form what? Carbon monoxide fully. So that means At this region, what is dominant? Carbon monoxide is dominant. That's the first part of the story. You need to understand we always get carbon monoxide at the bottom. Okay, if you want, you can add these two reactions also and get an overall reaction. But it would be two carbon solid reacts with O2 gas to form two carbon monoxide. Okay, so in that way we can get three reactions that can occur at the bottom part of the blast furnace. Should be right now. Now think about what I'm going to tell you. Now this carbon monoxide is not going to stay forever at the bottom of the bottom of this blast furnace. What will happen? It will try to go upward, isn't it? It will try to go upward since it is a gas. So always maintain a good airflow from the bottom. This carbon monoxide will move upward. Will move up. So let's say carbon monoxide is crossing this line. So it moved to the low temperature zone. What will happen to the stability of the carbon monoxide? It was stable at high temperature, but it will not be stable at low temperature. Isn't it? That means carbon monoxide will try to get oxygen and become carbon dioxide again, isn't it? And when it go up, carbon monoxide is no longer stable. Carbon dioxide is stable at this region. So now carbon monoxide need to become dioxide. You understand that point? Okay, so now there is a huge problem. The thing is, we don't have O2 at this region. Therefore, the reverse reaction of this one can't occur, whatever this process. Understand? And we don't have alcohols on it. Right? You can see here. So anyway, my point is that we don't have oxygen in this region. So now it can't become carbon monoxide, carbon dioxide, just by getting oxygen. Okay, we have a problem. Because why? Because we inserting air, this air is kind of regulated, controlled. And all the O2 molecules we are adding are consumed in this region. That's how we insert control rate. Right? So therefore, at the top region, we don't have O2. All the O2 are consumed to make carbon monoxide, and it is doing this reaction. You understand? So now carbon monoxide need to become carbon dioxide, but it don't have O2 to react. So what this carbon monoxide would do? It will try to react with something that already have oxygen. What is that? Fe2O3. Fe2O3. Fe2O3 hematite. Hematite, you can see in its formula, you have oxygen. Right? So carbon monoxide will do what? Will get oxygen from that one and become carbon dioxide. And at that time, what will happen to our Fe? It will become Fe metal. You get the idea? Huh? So hematite will give oxygen to carbon monoxide, and hematite will undergo reduction. Carbon monoxide will be oxidized, but not by getting oxygen from O2. It is oxidizing by getting oxygen from hematite. So now when carbon monoxide get what it wants, we also get what we want also. What is that? Iron. Fe. Now that's how iron extraction works. That's the story you need to remember. So start from here. Coke burns to form carbon dioxide. In coke, carbon dioxide and coke again reacts to form carbon monoxide, and that's the gas stable at this low region, bottom region. Because of that very high temperature, always carbon monoxide is formed 100% spontaneously. But since it is a gas, it should go up. When it is going up, stability of that carbon monoxide will become low. And carbon monoxide need oxygen from somewhere. But the problem is we don't have O2 at the top region. So carbon monoxide will get oxygen from where? From hematite. Okay, then hematite will reduce to Fe. That's the metal we know. So we have extracted iron. Okay, but that's the problem now. Now this reaction was there in your O-levels. And this is kind of an overall reaction. This reaction is not happening at one step. This is happening in several steps. For A levels, you can't write this reaction. And for A levels, what we need to give is the process happening step by step. First of all, if hematite react with carbon monoxide to form Fe3O4. Fe3O4. So what is this Fe3O4? Don't get confused. Fe3O4 is a mixture of oxides. If you add FeO and Fe2O3, what will you get? Fe3O4. So that means part now here all ions are at +3 oxidation number. And when it reacted carbon monoxide, part of it is converted to +2, but still we have +3. You get the idea? Part of iron is reduced to +2, not fully. Okay, that's why the formula was Fe3O4. We call it as ferroso-ferric oxide. Ferroso-ferric. Ferrous means +2, ferric means +3. Ferroso-ferric oxide. Understood? This is ferric oxide. Now ferric oxide becomes ferroso-ferric oxide. Then that Fe3O4 react with carbon monoxide again to form FeO. Now what has happened, Lamai, that remaining part was also reduced to Fe2. Okay, you have to show that one as a steps. And then finally, this FeO can react carbon monoxide further and become Fe. This is how carbon monoxide is reducing hematite. You need to give it in 3 steps, not by one reaction. And the reason for that is now these reactions are occurring at certain regions, certain temperatures. That's why we need to give it separate. There's no single reaction. Is that clear? Right. So those are the 6 reactions you need to remember at first. The 3 reactions for carbon related ones and the 3 reactions for hematite ion related ones. Okay, and let me tell you the next part first. And now we have to learn 4 additional reactions. So altogether, there are 10 reactions in the ion extraction. You can already understand 6. So now let's see remaining 4. Okay. So now we added cork. We say cork has 3 functions. Cork has 3 functions. One function is, first one is acting as a probe. That is the first function of cork. And the second function is making carbon monoxide, because carbon monoxide is the main reducing agent. It's a reducing agent. And the third function is carbon, this cork can itself react with FeO and make it Fe. Understand? Itself can react with carbon FeO. Okay, so this is the third function of cork. So it do this direct reducing also. Direct reducing agent also. Okay, so that's the third function of cork. So that's our 7th reaction. Is that clear now? So cork has 3 functions. So our 7th reaction comes as the third function of that cork. Understood that nicely? Okay, but remember, cork can't directly react with hematite. You can see it's not reacting with hematite. It is reacting with a intermediate product of the process, FeO. Understood? Remember that. And then we have 3 more reactions. But you can see we kind of used all 3 raw materials. From raw materials, we use only 3. We use hematite, use coke, we use atmospheric air. So one is remaining, limestone. So you already have Fe. So limestone was not involved in that process. Okay, so let me tell you what limestone is. And limestone is there to serve a specific function. Okay, first of all, and under this high temperature conditions, limestone, calcium carbonate will undergo thermal decomposition. It will undergo thermal decomposition to give calcium oxide and carbon dioxide. So we don't pay attention to carbon dioxide, anyway it will participate in the process. Right? But what is important for us is calcium oxide. Okay, let me tell you. This hematite we got from the ground. Isn't this something coming from the ground? Like I said, it will contain. It will contain what? It will contain, certain impurities. Name for them as impurities. Okay, so it's not always 100% hematite. You may contain SiO2, Al2O3, vanadium compounds, manganese compound, a lot. So we don't need them in this process. And having them is also make iron kind of less pure. Isn't it? So we are extracting a metal supposed to be having a good purity. Understood? I'm not telling we need 100% iron, but our iron amount should be high. Okay. So to make it kind of more pure, okay, to increase the yield, we need to remove those impurities, unnecessary compounds. Okay. So to remove those unnecessary compounds, we use this calcium oxide. Because with calcium oxide, you can react. With calcium oxide, you can react Al2O3, aluminum. Right? Then it will form CaLO2 twice, calcium aluminum. Okay. And with calcium oxide is reacting another impure compound, this iron or silica, SiO. It will form calcium silicate, CaSiO. And these two are not going to mix with Fe. Now, as the last product we get Fe, it is not going to mix with Fe. It is going to float on the top of Fe layer. Okay, so we call it as, you may have heard it before, slag. Slag. Understood? So it's not going to mix with Fe layer. It is floating on the top of Fe layer. And it is serving us another function also by the. Because once it is floating on the iron is not contacting with the upper region. Isn't it? Upper region contains air, O2, and many things. So iron is not going to react again with O2. Because of what? Because of the slag layer floating. Same way, if oxygen contacted with this Fe, what will happen again? It will become Fe2O3 and again the reverse thing can happen. Okay, so you get the idea. Can you understand the 10 reactions? The first 3 are about coke reacting with O2, then form carbon dioxide, and carbon dioxide will react with coke again to form carbon monoxide. This is the overall reaction. So 3 reactions. And then that formed carbon monoxide is reducing ferric oxide, hematite in 3 steps to Fe. And the coke can react a direct reducing agent with FeO, ferrous oxide. Okay. And that's our 7th reaction. And the remaining 3 is there because of calcium carbonate. First thing is its decomposition. And the latter 2 are removing the impurities, impure compounds, unnecessary compounds that were containing in iron ore, Al2O3 and SiO2. Silica and aluminum. These are called calcium aluminate, calcium silicate. They can be given them in MCQs also, so you need to remember the names. Calcium aluminate, calcium silicate. Is it clear? Huh? So that's everything about ion extraction. And like I said at the beginning, we must control the rates of inserting solid raw materials and gaseous raw materials. Why? What is the importance? If they ask you to explain the importance of that, but we can tell. Because if you change that thing, Or if you insert air more, what will happen? If you insert air more than the required amount, that O2 will go to this region and that O2 will combine with carbon monoxide before hematite does. Understand? So then that reduction of hematite will not happen.